This is Algebra 2, Unit 4, Lesson 5, the method of common bases. Now, there are very few algebraic techniques that do not involve technology to solve equations that contain exponential expressions, but we're going to look at the few known as the method of common bases. And it's just like what it sounds like. The method of common bases means each side of the equation has the same base. And we get, once the bases are equal, the exponents are equal. So, if I have 2 to the x equals 16, well, 2 to what power will give me 16? Well, isn't 2 to the 4th equal to 16? Yeah, so if 2 to the x is equal to the 4th, that means that x would have to equal 4. All right, 3 to the x equals 27. 3 to what power is 27? It would be 3 to the 3rd. So that means that x would equal 3 to make them equal. All right, 5 to the x equals 1 over 25. Now, how do we write 1 over 25 as a base of 5? Well, we know 1 over 25 is 1 over 5 squared. But if we want it to be in the numerator, how would we write 5 squared? Well, if I want to move it up here, do its reciprocal, it would have to be 5 to the negative 2, because that's equal to 1 over 25. So that means that x would equal negative 2. All right, 16 to the x is equal to 4. All right, well, let's see. 4 is really 4 to the 1st. How do we write 16 as a base of 4? Well, 16 is actually 4 squared. Well, power to a power, what do we do with the exponents? We would multiply them. Power, power. So this is actually going to be 4 to the 2x is equal to 4 to the 1st. So since the bases are equal, the exponents must be equal. 2x is equal to 1. And divide by 2, x is equal to 1/2. So x is equal to 1/2 when we do this. So 16 to the 1/2 is equal to 4. So there we go. So the trick is get the same base. Once you have the same base, set the exponents equal to each other. All right, so in each of these cases, even the last, more challenging one, we could manipulate the right-hand side of the equation so that it shared a common base with the left-hand side of the equation. We can exploit this fact by manipulating both sides so they have a common base. First, though, we need to review exponent law, which we were just talking about a minute ago. 2 to the cubed raised to the x power. Power to a power, you multiply. This would be 2 to the 3x. Okay? 3 to the 2 to the 4th power, 3 squared 4 to the 4x power, would be 3 times 2 times 4x would be 3 to the 8x. This one, this is going to be 5 to the negative 1 times 3x minus 7. Make sure you distribute the negative 1. Negative 3x plus 7. And then this one, 4 to the negative 3 to the 1 minus x squared, would apply to both. So it would be negative 3 times 1 minus x squared, negative 3 plus 3x squared. And that would be equivalent. All right, so using that fact, let's see if we can get a common base for each side. Now, what base can we write 8 as? What raised to what power? Well, 8 would actually be 2 to the 3rd. And that's raised to the x power. All right, what is 32? 2 to what power is 32? It would be 2 to the 5th. All right, now, let's get our bases the same. Power to a power, we multiply the exponents. 3x equals 2 to the 5th. So since the bases are the same, the exponents are now the same. 3x is equal to 5, so x is equal to 5/3. And if you want to check, 8 to the 5/3 raised to the 5 divided by 3. Look at that, it's 32, and it works. All right, so the trick is get the same base and then set the exponents equal to each other. All right, we have 9 and we have 27. What can we write 9 as a base of? As a base of 3. 3 squared is equal to 9. And then 2x plus 1 is on the outside. And 3 to what power is 27? 3 cubed is 27. All right, power to a power, multiply the exponents. So remember, this has got to distribute through here. So this will be 3 squared to the 2x plus 1. 2 times 2 is 4x. 2 times 1 is 2. Equals 3 to the 3rd. So since the bases are now equal, the exponents are now be equal. 4x plus 2 is equal to 3. So 4x is equal to 1. And x is equal to 1/4. So there is your base. Okay, now here's a little more complicated one. 125 to the x equals 1 over 25 to the 4 minus x. All right, so what base could I write 125 as? How about a base of 5? 5 to the 3rd is 125. raised to the x power. All right, now how do I write 1 over 25 as a base of x, or a base of 5, excuse me. Remember, we did it back here. 1 over 25 was right here with 1 over 5 squared, which is 5 to the negative 2. All right, so that's equal 5 to the negative 2 raised to the 4 minus x. Power to a power, multiply the exponents. That would be 5 to the 3x. Distribute this. 5 to the negative 8 plus 2x. Watch your signs there. The bases are now equal, so the exponents are equal. 3x is equal to negative 8 plus 2x. Move the x over, and then you get x is equal to negative 8. And there we go. We've got it. All right, so if you can get the bases the same, set the exponents equal to each other. You may have to do some manipulation with the same base to get that to work. All right, so which of the following represents the solution set to the equation 2 to the x squared minus 3 equals 64? Well, this has got a base of 2, so let's see if we can write 64 as a base of 2. So 2 to the x squared minus 3, 2 to what power is 64? It would be 2 to the 6th is 64. So that means x squared, or 2 to the x squared minus 3 is equal to 2 to the 6th. Set the exponents equal to each other. Move the 6 over. We get x squared minus 9. And that factors as x plus 3, x minus 3 is equal to 0. X plus 3 equals 0. X minus 3 is equal to 0. So x is equal to 3, and x is also equal to negative 3. Now, you could have just moved the 3 over and done x squared plus equals 9, but remember, there are 2 answers when you take the square root. So it's going to be number 1. This technique can be used in any situation where all bases involved can be written with a common base. In a practical sense, this is rather rare, yet these type of algebraic manipulations help us to see the structure in exponential expressions. So let's look at the more challenging problem next. Okay, 2 exponential curves, y equals 4 to the x plus 5 over 2, and y equals 1/2 to the 2x plus 1 are shown below. They intersect at point A, so they intersect right here. A rectangle has one vertex at the origin, which is right there, and the other at A as shown. So this is a vertex, and the other is a vertex, and we want to find its area. Okay, so fundamentally, what do we need to know about a rectangle to find its area? Well, we know its area is equal to length times width. Length times width is area. All right, so how would knowing the coordinates of point A help us find the area? Well, that would give us the length and the width. So the y-coordinate would equal the height, because that would be the distance from here to here. That would be the height, or the width. Okay, and the x-coordinate of point A, whatever that would be, would give us this value down here, and that would give us the base. All right, so if these two curves create this point, that means that they would be equal to each other. So if we could use substitution, algebraically, 4 to the x plus 5/2 is equal to 1/2 to the 2x plus 1. All right, so let's see if we can get this to be the same base. All right, now what can I write 4 as? Well, I can write it as a base of 2. So that would be 2 squared raised to the x plus 5/2. All right, now how do I write 1/2 as a base of 2? 1/2 is a base of 2. If I moved it up to the numerator, we're making a negative exponent. So that would be 2 to the negative 1 to the 2x plus 1. Okay, power to a power, multiply the exponents. So that's going to be 2x plus 5/2 times 2 is 5. Oops. And then distribute the negative 1. This is going to be 2 to the negative 2x minus 1. So with the same base of 2, I can now set the exponents equal. 2x plus 5 is equal to negative 2x minus 1. Solve for x. Move the x over here. That gives me 4x plus 5 is equal to a negative 1. Subtract the 5. 4x equals negative 6. Divide by 4. X equals negative 6 over 4, which is negative 3 over 2. Okay, so we now know that this point right here, the x value is going to be at negative 3 over 2. All right, so if my x value is negative 3 over 2, that means the distance from here to here is going to be 3 over 2. Okay, because I go out this distance and then up. All right, now how do I find the y? Well, to find the y, I would plug into one of the equations. Does it matter which one? No. All right, so if I take the y one, I'm going to take this one. 4 to the negative 3 over 2 plus 5 over 2. That's going to give me 4 to the negative 3 over 2 plus 5 over 2 is 2 over 2, which is 4 to the 1, which is equal to 4. So that means my y-coordinate is going to be 4, and this distance right here, we go over 3 over 2 and then up 4. So my area will be the length times the width. 3 over 2 times 4. So the area will equal 6. 3/2 times 4 is equal to 6, and that is your area. Okay, so by knowing the exponential function, setting them equal to each other, we can figure out what the coordinates of A would be. All right, let's try another one. Actually, let's save exercise 6 for the next class. See if you can figure it out. At what x coordinate will the graph of y equals 25 to the x minus a intersect the graph of y equals 1 over 1/25 to the 3x plus 1? Show the work that leads to your choice. So see if you can work that out and see what x is going to equal. And we'll go over it the next class.